Hello everyone, welcome to the 14th lecture for our course Irrigation Engineering and Hydraulic Structures. So today lecture is very important because we are starting our design phase of canals, right? The first theory we are going to start today is known as Kennedy's theory for designing of alluvial canals. Okay, so the first theory we got is Kennedy's theory, and it is for designing of alluvial canals. So we are going to cover this theory in 3 lectures. In first lecture we will just introduce the important points related to Kennedy's theory and designing of alluvial canals. The first step, lecture number 14. In today's lecture we will introduce the theory, and in second lecture, which will be our lecture number 15, in lecture number 15 we will discuss and try to understand the design steps for Kennedy's theory, and in third lecture, which will be lecture number 16, we are going to solve some numerical problems based on Kennedy's theory. So these 3 sections will make us compatible to understand the Kennedy's theory, and we will come to know how we can design alluvial canal based on Kennedy's theory. Okay, so let's move forward and see what we got for today's lecture. As we have discussed previously that we have divided canals on the basis of their lining, right? Unlined and lined canal. So for the purpose of, let me change the color. So for the purpose of designing we divide canal into 2 main types. So every time whenever we will design a canal, we will design either based on either it is unlined canal or lined canal, right? We have already defined unlined canal and lined canal. Let me revise it for you guys to remind it again. So those canals, unlined canals are, what are unlined canals? Unlined canals are those canals which are constructed on alluvial or non-alluvial soil, right? They are constructed directly on alluvial or non-alluvial soil. So that means that these type of canals can be eroded easily because they are made up of soil, right? Alluvial and non-alluvial soil. So again, we have already discussed all these things, but for those who are listening this lecture first time, I am revising it. Alluvial soil. What is alluvial soil? Alluvial soil can be your sand, silt, or clay. Okay. And what is non-alluvial soil? Non-alluvial soil can be maybe solid rocks. It can be your boulders, or maybe coarse material. If it is made up of coarse material, if your canal is made up of these material, then you can call it non-alluvial. If it is made up of sand, silt, or clay, then it is alluvial. Got it? So this is the difference between alluvial and non-alluvial canals. So the other thing you must know about unlined canal is that, as we have said, that as unlined canals are made up of sand, silt, or clay, right? If this canal is made up of sand, silt, or clay, what is going to happen? If water will pass through this canal, obviously it's, what is this? This is your side slope, right? And what is this? This is your bed. What is going to happen? Let me change the color. Okay. So if water will pass through this canal, and if this canal is made up of sand, silt, or clay, obviously the water will erode the side slope and bed of the canal, right? When it erodes your canal, the dimensions or cross section of the canal will change. And what will happen? The dimension will obviously increase, right? If it erodes your sides, obviously it will, your shape of canal will change, and it will become something like that, right? So this part is being expanded. This cross section of the canal will increase. What will happen? The cross section of canal will increase. Cross section of canal will increase due to erosion, right? So what this is called? There is a term to define this. When this happens, we call this is known as scoring. This is defined with a term known as scoring. Okay, so what is scoring? Whenever the shape of your canal will change and it will increase the cross-sectional area of the canal, then that is called scoring. And this scoring happens because of the erosion. Okay, the second case can be lined canals. Actually, the lined canals are those canals, as we have discussed, are those canals which have been constructed by using any binding material such as cement, tiles, stones, right? we cover the inner face of the canal, like this side slopes, and the bed of the canal is covered with a material, and it will stop the process of seepage, right? So what is this? This may be some sort of let me change it, some sort of material that cannot be easily eroded. Got it? Like cement or tiles or stones. So what is going to happen in such cases? In such cases, if water is flowing in the canal, obviously scoring will not occur here, right? There will be no scoring because we have used a material which stops the erosion. So if there is no erosion, that means that there will be no scoring. Then what is going to happen here? In this case, what will happen is that whenever water will flow in the canal, as we know that there are particles, right? There are particles within the water. So when water will flow with less velocity, if the velocity is low, what is going to happen? Then in that case, these particles will settle down, right? Settle down at the bottom of the canal. So what will happen? Particles of sand will settle down at the bottom of canal, and it will ultimately reduce the size, or you can say cross section, of canal. Okay, we call this, there is a term to define it, we call it let me write it here. Yeah, silting. Okay, I hope now you can differentiate between silting and scoring. Silting and scoring. Got it? We got two terms, silting and then scoring. Whenever there is silting, the dimension of your canal is going to, the cross section or size of your canal is going to be increased. Scoring will cause your canal to be expanded, right, due to erosion. But in case of lined canals, there will be no erosion, right? If there is no erosion, there will be no scoring. If there is no scoring, that means that the particles, whenever there is velocity is less, the particles in the water will try to settle down with the passage of time, right? When they settle down, obviously they will decrease the cross section of the canal, and that process is called silting. Got it? So what is going to happen when scoring occurs? When scoring occurs, this level of water will come down, right? Because the size is increased. But in case of silting, the level will go further up. Got it? Because particles have been settled down and it has decreased the cross section of your canal. So for lined canal, you can write let me choose the blue color. In lined canal, the side slope and bed are covered with a material which cannot be eroded easily, right? For example, concrete, or maybe tiles, maybe stones. Okay, hence the boundary of lined canals are rigid in nature, right? Will be rigid in nature. That is the reason they are also known as rigid boundary canals. Got it? So the point is that we need to, let me first make a portion to divide these two parts, lined and unlined canals. Okay. So in the case of lined canals, we have discussed a few more things. In lined canals, there are two types, right? There were alluvial canals and non-alluvial canals. So in case of alluvial canals, their surfaces are made up of soil, right? Side slope and bed are made up of soil. So you can say that alluvial canals are soil surfaced, and non-alluvial canals are hard surfaced or rock surfaced. So some important points related to alluvial canals and non-alluvial canals is that you need to note it down. For alluvial canals, we can say that alluvial canals, they pass through alluvial soil. Alluvial soil strata. Second point related to alluvial canals is that silting or scoring both may occur here. Why? Because their boundaries are made, or you can say composed of silt, sand, loam or clay, right? That is the reason erosion will occur here, and you can face the problem of silting and scoring both. But in case of non-alluvial canals, as they are made up of rock surface, you can say that they pass through hard strata. Okay, and because of the hard strata, no silting will occur. And their boundaries are made up or composed of rocks, boulders or coarse material. Got it? So in our case, as our main topic is Kennedy's theory, right? And we said that Kennedy's theory is for designing of alluvial canals. So till now we have discussed different types of canals, but Kennedy's theory is based on designing of only alluvial canals. So Kennedy's theory is only going to help us to design alluvial canals. This one. So we can say that Kennedy's theory is only used to, let me write this in next line, used to design alluvial canals, right? Those canals in which there will be silting and scoring both. So let's move forward and try to discuss few more important points. Now we are going to consider this section only, right? So here we need to note down few important points, make it as notes. The first important point you must know is that Kennedy and Lacey's theory. We will discuss this next. This is our next theory. So both the theories, Kennedy's and Lacey's theory, are used to design only alluvial canals. You need to remember this point. Second important point is that they means Kennedy and Lacey, they do not give us the exact calculations, or you can say these theories do not give us the exact calculations. Why? They only give us hypothetical. They only give us hypothetical values. The reason is that because these both theories are based on some hypothesis, right? And till date there is no any proper method, theory or formulas to design alluvial canals. So still we are using the Lacey's and Kennedy's theory to design the alluvial canals. Okay, these were few important points. You can be asked these points in maybe an interview, or you can get these points in some sort of exams. So other few more important points you need to note down are, the first thing is that, let's write them with green color. Okay, the first point is that as we know that, and we have already discussed, we usually face two problems, right? Two, you can say, major problems in alluvial canals. What are those problems? scoring and silting. You must remember this. And the second point is that alluvial canals will be used where irrigation is done through divergence schemes. Got it? For example, a river. Let's take an example. For example, river divergence of water for crops of water for crops. So one important point we have missed here is that for alluvial canals are preferred for diverging irrigation, and non-alluvial are preferred for storage irrigation. Okay, so this was the difference. The next point, important point we must know is that, that's it. These were two important points, and you can say that or we can use alluvial canals where water flows continuously without any breaks. Okay, let's move forward and discuss few more important points. So the main hypothesis. So let's start with the hypothetical step for alluvial canal design. The hypothetical step, you can write it down. As we said that these designs are based on hypothesis, right? Hypothetical step for an alluvial canal design. It says that as per these theories, by these I mean Lacy's and Kennedy's both theories, right? For these theories, if water is running with a certain velocity and having sediments in suspension, then it may show the problem of scoring or silting. Got it? So there can be three cases which we can face. Let's draw a figure first and then try to see what can be the three cases. Let's say we have a cross section of a canal. There can be three cases. The first case can be velocity in the canal can be velocity in the canal velocity in the canal let me use different color for this. The first case can be, let's say, V1. Velocity in the canal can be greater than V, or second velocity that can be less than V. And what is V? This is V. Let's first draw the figure and then we will discuss each and everything one by one. Let's say V is the velocity. V is the velocity when there is no silting and no scoring. In that condition, the velocity which will be in the canal is known as V. Okay. So in one case we can have our velocity greater than the V when there is no silting and scoring. It can the velocity can be greater than V. What does this case means? This case means that if our V velocity in the canal is greater than V, as we have defined what is V when there is no silting and scoring, right? So if V1 is our velocity is greater than the than V, then that means that there is silting, right? There will be no scoring, because if velocity is greater, that means that it is going to, if velocity is greater, obviously it will, what it will do, it will do the erosion, right? It will erode sides and bed of canal. So if it erodes sides and bed of canal, that means the silting will occur. If velocity is less than V, that means that, as we have already discussed, if velocity is less, then what is going to happen? The particles of sand present in water will settle down, right? If they settle down, what we call it? We call it scoring. Got it? So now you can easily say that if the velocity is less than V, then scoring will occur, right? If velocity is greater than V, silting will occur. Got it? And what is V? V is the velocity when there is no silting and no scoring. Are you getting my point? So this is the main difference. There can be three cases. Either there can be silting, either there can be scoring, or there can be no silting and no scoring. If there is no silting and no scoring, we represent it with V. If there is silting, we represent it with V1. If there is scoring, that is V2. Got it? So there can be 3 conditions. On the basis of this, we are going to note down few more important points. What are they? We can say that if water is not full charged with silt, then it will start to score, right? Score the bed and side slope of canal it will happen until it is fully charged. Second important point is that if all these points are based on the above diagram which we have discussed, if velocity is less, then silting may take place, and if velocity is high, scoring may take place. Okay, we have already discussed these points, but we are actually revising them here and making notes. Next point you need to note and remember, this silting and scoring in the canal may lead to the reduce in design discharge capacity of canal. Okay, we have done the numericals based on the discharge capacity of canal, right? So if there is silting and scoring in your canal, obviously it is going to reduce the quantity of your design discharge capacity. Got it? If you go into the previous lectures where we have done the numericals, you will understand this point, because from the head of the source to the head of the water course, there are some sort of reductions, right? That can be maybe due to seepages or evaporation losses, or that can be also because of silting and scoring. So they are going to reduce the discharge design capacity of your canal. So now for proper designing, what we need to do? Let's write down few more important points. So these are very important points. They are going to help us in the designing steps or designing phase of the canal, and they are also very important when it comes to different exams. Okay, so for proper designing of canal, there should be no silting and no scoring. Got it? So if you want to do proper designing of canal, then there should be no silting and no scoring. So if there is no silting and no scoring, such canals are known as stable canals, or we can call them regime canals. Okay. So what are the conditions of a stable or a regime canal? You can say that the conditions will be either silting is equal to scoring. If silting and scoring are equal, you can call that sort of canal as stable canal or regime canal. Or second condition is if there is no silting and no scoring. Got it? So these two conditions, wherever you find these two conditions, then you can say such canals, you can call such canals as stable canals or regime canals. Got it? So let's move to the next point. Next point you need to remember is that a canal for which silt grade, I'm using three terms. Please try to focus on these three terms. A canal for which silt grade, silt charge and discharge are constant. These canals are said to be in regime condition, or you can say that these canals are in stable condition. Got it? I have mentioned three terms here. What are those three terms? Silt grade, silt charge and discharge. Okay, so let's see what are these three terms. The first term is silt grade, right? Silt grade actually means the size of silt particles. Okay, so if the size of these particles is constant, right, then you can say that the silt grade is constant. Got it? That means that each and every particle size will be same. Like if the particle size is this one, then the other particle size will be same as size of this particle. Okay, let's say they are same. Same particle size or same silt particle size. Then you can say that the silt grade is constant, because we have defined as a canal for which silt grade, silt charge, discharge are constant. Then these canals are said to be in regime condition or stable condition, right? So silt grade means if all the silt particle sizes are same or constant, then your silt grade is constant. And the second term we used is silt charge. Okay, what does silt charge means? Silt charge means the quantity of silt particles. Okay, are you noticing the difference? Silt grade means size of silt particles, silt charge means quantity of silt particles, right? So again, if the quantity of silt particles is constant throughout, then you can say that the silt charge is constant. Okay, the third term you used is discharge, right? What does discharge means? Discharge, we know the formula for discharge, Q is equal to area into velocity, right? So if your Q is constant, discharge is constant, that means that the area, cross-sectional area will be constant too. So if cross-sectional area is constant, that means that your velocity is going to be constant. Got it? So wherever these three things are constant, your silt grade, your silt charge and discharge, these are constant. That means that your canal is in the condition of is in regime condition or stable condition. Got it? So this was next important point. Now let's move forward. And these were few important points you need to remember. And in next video, we are going to discuss the design. In next lecture, we will discuss the design steps for Kennedy's theory for designing of alluvial canals. Okay. So that's it for today's video. We have discussed very important points. Let's try to revise them in 1 or 2 minutes so that things will become more easier. So our basic topic is Kennedy's theory for alluvial canal design, right? So in first part we just introduce our designing phase of alluvial canals, where we have discussed unlined and lined canals. What is the difference between unlined and lined canals, and the terms scoring and silting. These are two important terms. And then we have defined some properties of lined canals and unlined canals, and then we have divided unlined canals further into two types, alluvial canals and non-alluvial canals. And our main design is based on alluvial canals, because Kennedy's theory is only used to design alluvial canals. Similarly, the Lacey's theory is also used to design alluvial canals. Okay, so these canals, alluvial canals, are preferred for divergent irrigation, diverging irrigation, and non-alluvial canals are preferred for storage irrigation. And then we have discussed some important points related to the both theories of Kennedy's and Lacey's. They are used to design alluvial canals, and these theories do not give us exact calculation, and they are based on hypothetical theories, and we need to remember these points. Till date there is no any proper method, theory or formula to design alluvial canals, so still we are using these two theories to design alluvial canals. Okay, then we discussed about these few more important points, and then we have discussed these important points to find out either there is silting or scoring. If your velocity is greater than V is no silting and no scoring condition. So, and this no silting and no scoring condition is known as stable condition, right? So the velocity in stable condition, if your velocity is greater as compared to the velocity in the stable condition, then silting will occur, because if velocity is higher, that means that it will erode your sides and bed, and then silting will occur. And if velocity is less as compared to the velocity in the stable condition, then scoring will occur, because the particles of the sand in the water will settle down. So these were few important points we have discussed. And then we have discussed these three important terms: silt grade, silt charge, and discharge. And we have also discussed what is stable canal, what are the conditions of resigned canal or stable canal. And then we have discussed these three important terms: what is silt grade, silt charge, and discharge, right? Three important terms: silt grade, silt charge, and discharge. So that's it for today. See you guys in next video with the design steps of alluvial canal. Till then, goodbye.